See what you remember. Now, my name is Kevin Knuth. I'm a professor of physics at the University at Albany. I do experimental work, theoretical work, and computational physics. I don't know what box to put myself in, and nobody else ever knows either. I've worked to study UAPs with UAPX, and I'm not going to talk about UAPs at all today. Sorry. We're going to talk about other things. And and I'm going to talk about the universe. I went into physics because I wanted to understand how the universe works. And so this talk is mainly just some thoughts about that. I don't know how to advance. Here we go. This thing may do it. There we go. So I want to have a successful talk, and so I'm going to follow this advice. There are 2 rules for success. One is never tell anything, never tell everything you know. So you can ask me questions later. And so here we have the evil villain, the materialist worldview. And we really rail on this guy a good bit. And over here I have a picture of what's called the standard model of physics. This is what everything's made of, according to the materialist worldview. But the problem is that matter matters. Matter is a big deal. It makes a big difference. It matters with you. You're made of matter. I mean, this hurts. I mean, matter makes a difference. And so there's a lot to be said for the materialist worldview. It's really helped us understand a lot about our universe. And so what are we to make of this, and how are we to make some progress? What science does is science really aims to describe the universe to the degree to which accurate predictions can be made. And what we call the hard sciences are sciences that are quantitative, right? Where we assign numbers to things. Why do we even assign numbers to things? Where does that even come from? We have this weird belief that mathematics is actually part of the universe at this point. We assign numbers to things so we can rank them. So I can tell that, this is heavier than this is. Well, I give this a bigger number than this. And now you can do much more than rank them. You can actually rank differences between things. And so it's very useful. But it's really just a description. It's a description where you're mapping things to, or properties of things to numbers. That's what you're really doing. And when I come to this meeting, or I've been to this meeting before, or seen other people talk on this topic, many of my colleagues here are in the humanities, and I often hear some apology. Oh, I'm sorry, I'm from the humanities. Like there's something wrong with being from the humanities. The problem is that the humanities are important too. It's a different type of description. And actually, when we're studying the universe, when we study things, we have to decide what we want to describe. What aspects are important? So here's a horrific picture. How do you describe this? There are many ways to describe this picture. There's many ways to understand what's going on. And all of those ways are important. And some of these descriptions are incommensurate. So you can be a physicist or a chemist. Well, a person's burning. Oh, that's very simple. A person's body is made up of organic molecules, and they're undergoing a chemical reaction with the oxygen in the atmosphere. Well, you can't see the oxygen in the atmosphere, but that's the materialist description of what's happening. Does that really describe what's happening in this picture? Depends on what you want to describe or what you want to understand. There's a person protesting a social injustice. So to describe what's happening, you have to understand the religious and social interactions involving Buddhists in South Vietnam in 1963. And once you understand that, you have a better understanding of what's going on in this picture. And just much like the oxygen is invisible in this picture, those social interactions are also invisible. They're not less important. Another perspective, a person's burning yet not panicking. A man sits calmly in meditation as he burns, which we all recognize should be a painful, terrifying event. So this is described by the monk's conscious control over the matter which makes up his body. What's happening there? That's another description. And each of these descriptions are relevant and important. We have to look at all of them to really understand, to get a full picture of what's going on. And taken separately, they can be incommensurate. So yes, matter matters. Materialism matters. Religious social studies matters. Consciousness matters. It all matters. It's all important. And that's what we're doing here, which I really appreciate. And people have long wrestled with this problem of description. And one of the problems with this is we have a hard time often separating our description of reality from reality itself. We very often come to believe that our description of reality is actually reality. This is Ed Janes, a physicist, gave this a name. He called it the mind projection fallacy. And you see this in physics happening as well, where your own imagination, you come to believe that this is a real property of nature, or your own ignorance, you come to believe that that means nature is indeterminate. This is related to reification, which in philosophy, as I understand it, is treating an abstraction as a real thing. And that's a bit of a problem. So you see this in quantum mechanics. Quantum mechanics is hard because many people don't understand it. Even physicists who study it don't always understand it. And Werner Heisenberg here stated the Heisenberg uncertainty principle, where you cannot know both the position and speed of a particle with perfect accuracy. There's the equation for it. So the delta x is your measurement of the uncertainty in position. And then you have an uncertainty times the uncertainty in your momentum that's always going to be bigger than another number on the right. So if you have a very small uncertainty in the position, which means you know pretty well where an object is, then you have to have a very large uncertainty as to what its momentum is. Well, there's something weird about this. Now this drives people nuts, or drives scientists nuts, because, well, wait a minute, how can a particle have a position and a momentum? How can it not have a position and a momentum at the same time? And part of that confusion is coming from the idea that a particle has a position and the particle has a momentum. Those are descriptions. And don't confuse your description of the particle with what the particle is or does or has. We don't actually know what a particle is. Nobody knows what a particle is. And so what happens to the person who's running alongside a very fast particle and knows its position very well, whereas a person who's standing here sees a particle go flying by at a very high momentum. There are different perspectives that different observers can have, and what you realize when you look at this very closely, and this is a lot of Einstein's work is based on this, is that the position and the momentum are observer dependent. The position and momentum of a particle don't just depend on the particle. They're not possessed by the particle. It's actually a description of the relationship between a particle and observer. So it can't just be owned by the electron. And that's when you could start to sort this out. So the key to understanding the Heisenberg uncertainty principle is that positions, momentum, energy, all of these quantities are not possessed by a particle. They're quantities that describe relationships. And these two descriptions, the description of position and the position of momentum, are incommensurate. You can't have one description and use that at the same time as the other description. And that's actually what the Heisenberg uncertainty principle is telling you. And we actually know this in another field, in signal processing. So if you've done work as an electrical engineer and have done signal processing with frequencies or signals, like time series signals, where you look at the variation of a sound signal in time, or you can look at the frequencies of that sound signal. they follow what's called the Fourier uncertainty principle, which is the same equation. You cannot describe a signal in time at the same simultaneously when you describe it with frequencies. Those two descriptions are incommensurate. That's all that's going on. There's no weirdness about quantum mechanics. The weirdness is that we forgot that we were describing things, and we took that description and said that's part of reality. And it's important to keep that separate. So once you appreciate this, once you realize that our physical concepts are actually descriptions, and that the goal of science is to make predictions about these descriptions, then you can do something quite interesting. You can look at describing a physical system, and you can look at all the possible ways you could possibly quantify it. How are all the ways you could use math to describe it? And sometimes you find out, in some cases, you find out there's only one way to do it that's logically consistent. And when you do this, you can actually derive the laws of physics from scratch, just from pure thought, which is a little surprising that you can actually do this. In the second paper here, when I had that published, I had a reviewer comment. It said, "I can't believe that you can just derive the laws of quantum mechanics from pure thought," which is what the author apparently just did. and I thought, yes, you get it. That's exactly what happened. Because I'm not deriving physics, I'm deriving the possible descriptions we could use possible mathematical description we can use to describe a physical system. If you could derive the actual reality from pure thought, then that's a whole different ball of wax, right? That would be interesting. Maybe that's possible too, I don't know. So what are the laws of nature? We don't actually know what a law of nature is or what it means to be a law of nature. So this is this also becomes very contentious when you work in foundational physics. So we've heard, so in this first part I mentioned how people in the humanities will often apologize to some degree about looking into an area where there's people in hard sciences also looking into it, like UAPs, and I noted that they shouldn't do that. But if you want to see something really horrific, have you ever seen a physicist talk about literature? And that's what I'm going to do next. So I'm sorry, but not sorry. All right, so here's, I'm going to talk about this book. I chose this book, The Little Prince, because it's a nice book, but it's also been translated in many different languages. You could do the same thing in other languages if you wanted. So how does a physicist look at literature? Like I said, this is going to be pretty horrific. I'm going to do the simplest thing. I'm going to literally just count. I looked at the first chapters. Count the number of letters, the number of syllables, the number of words, the number of noun phrases and verb phrases and sentences and paragraphs and chapters. I'm just going to count them. We're going to make it quantitative, right, in the crudest way possible. So here's a sentence from the book. The grown-up's response this time was to advise me to lay aside my drawings of boa constrictors, whether from the inside or the outside, and devote myself instead to geography, history, arithmetic, and grammar. So here you can see that I took the first part of this, the first line here, and I have boxed in with green all the letters. I've boxed in with blue the syllables, and boxed in with the words. Is it 8 words or 9 words? I don't really know what to do with grown-ups. I counted it as 1. All right, so so one thing you'll notice here that's interesting is that this is hierarchical. The letters group together to make syllables, the syllables group together to make words, right? It's a hierarchical. And you see this in nature a good bit. In fact, In fact, last night at the movie, we heard about the microcosm and the macrocosm. Now, at the microscopic scales, physics looks very hierarchical. In fact, we have a ranking of length scales that starts with the classical electron radius. This is one of the smallest. And then the next level, which is 130 times bigger, would be what's called the Compton wavelength. That's the wavelength of a photon that has the same energy as the rest mass of an electron. And then the next level up from that is called the classical Bohr radius, which is basically the radius of the hydrogen atom, which is, again, 137 times the previous one. It's actually that same number, puts them into different levels. And now what happens once you make atoms, you start to make molecules, and things get very messy. Things start interacting at multiple scales. So at the really low scales, things are pretty independent and pretty separate. You use different physical theories to describe what's going on. Quantum field theory, relativistic quantum mechanics, quantum mechanics. But once you get up into molecules, it gets very messy. And we'll see that here too. But at the large scales, things become simple again, even in the real world. So we have planets going around stars, stars form galaxies, galaxies form clusters, they form superclusters, and those are pretty hierarchical again. But at the mesoscopic scales, meso meaning medium, the medium scales, this is the scale we live at. We live at the mesoscopic scale. And things become complicated. So here you see that if I'm going to roughly group what are like noun phrases and verb phrases, you see these things are all nested, right? So the grown-ups response this time, that's one big noun phrase, but it has another one in it. And then we have a verb phrase that's constructed from a bunch of noun phrases. It's very messy, very loopy. And we saw that in Gary Nolan's talk yesterday when he was showing the molecules working together to make proteins. There's a lot of interactions going on at many different scales, and that's what's happening here in the literature. Same thing. A little easier to understand here, though, perhaps. Douglas Hofstadter, in his great book, Gödel, Escher, and Bach, talks about this as he describes them as ornate and fancy nouns, and you can create larger noun phrases by using these looping structures. So you could begin, and you come up with an article. Oops. Use an article, the, an adjective, the blue, noun, alien, and end. The blue alien, that would be fine. So there's an ornate noun, or I can have a more complicated one, the blue alien from the big red star Altair end, right? You could do something like that. So you can come up with more complicated nouns this way. So in the low scale, in the small scales, you have hierarchical structure. The mesoscopic scales, things become very messy, and you get loops. And the high scales, you get hierarchical structures again. And that seems to be a pattern. So here's another example of this as well, and you can see some of the looping going on. All right, so where am I going with all this? Well, I gave these things, I counted all of these things. So what are these numbers? Here are the numbers. The ones in parentheses I'm a little uncertain about. And you can see, yes, there's lots of letters. 2 in the first chapter. I only analyzed the first chapter because figuring the noun and verb phrases was difficult for me. Growing up, I hated like 3 things. I hated English and I hated statistics, and here I'm using both. So, and I do both in my real job all the time now. So. I'm glad I didn't know that when I was young, that would be the case. So what happens if you plot these? This is a log plot. This is the number of occurrences. I'm giving the letters a level of 0, so that's the number of letters, number of syllables, number of words, number of noun phrases, verb phrases, sentences, paragraphs, and chapters. The chapter one's off the line here because I only looked at one chapter. I didn't take into account the whole book. But wait a minute, why are these all on a line? That's kind of weird. Now, I didn't discover this. Eduardo Caianiello, a physicist from Italy, discovered this back in the 60s. And I think, as far as I know, is probably the only person who's ever published on this. Now what's going on weird, so what's weird is there's a few weird things happening here. At the lower levels, we saw that it's quite hierarchical. The mesoscopic levels, we know that there's loops and it's complicated. And then up here, it's hierarchical again. Paragraphs make chapters, yet they're all still on the same line. So even with all the weird complications you have going on with fancy nouns and ornate nouns, right? That's a little surprising. There's something even more shocking. When the author, Antoine de Saint-Exupéry, wrote the book, what did he do to write it? Well, he figured out what words to use. He figured out the phrases to use and the sentences to use. So he basically, the author, was in control of everything from here to the right. The author didn't control the syllables and couldn't control the letters. That's controlled by society. Why are these 2 points on the same line as the rest of these? How in the world is it that the author's choice in words gives you a straight line that goes along with the 2 points at the end that society, that the English language in this case, because it's a translation, determined? What's the dynamics here? Why are they on the same line? I don't have a theory for this, and I don't know anyone who does. This is kind of shocking. This is an anomaly that you can all go find yourself. You can go do this yourself this next weekend if you like. So what you see is, another way to look at this is there are correlations across the whole text. The text is correlated. Everything's correlated in some sense, right? And I've noted that in watching, watching David Lynch films is a good example. Did you ever try to explain to somebody what Lost Highway was about, or Mulholland Drive? That is incredibly hard to do. What happened? What is the movie about? Well, it's, I don't really know. I mean, it's kind of the feeling you get. And what he's doing there, what makes it unsettling, is that the movie is correlated very well at the small scales. From moment to moment, you can follow what's going on. But in the higher scales, they're not correlated. So you don't know what's going on at the larger scales. So the correlations are all off on his movies, and that makes them unsettling. They're not natural. It's weird, right? And so I think that's what's going on in some of his movies. There's a physicist's attempt to understand filmography. I should be apologizing a lot here. So these highly correlated behavior is common of complex systems. You'll see this in complex systems all over. And in fact, could this explain what goes on a lot in the universe? We like to think of ourselves as independent things, but we're part of a community. We're part of an environment. We're part of a universe, and so you've got your own personal experiences here, and then you've got the world around you at a higher level. There are correlations there. You're part of the world. You're interacting with it. And what's even going on at the higher levels, I don't even know. It's too big for me to even think about. But could this be where a lot of synchronicities come from, this correlation? You're not alone in the universe, but when important things are happening to you, there are going to be correlations elsewhere in the universe. It's all correlated. highly correlated. So what if synchronicity, what we see as synchronicity, when you recognize that correlation, there is no reason that should be happening, but somehow it's related to this thing that's happening with me. You don't see the correlation. I mean, you see the correlation, but you don't know why or how. And it's surprising and shocking and stunning. But we have an example of this. Here's this correlation right here. The author chose these words. The author didn't control this. Somehow this is correlated. We don't know how. So we have an example of a synchronicity-like anomaly in written language. You can do this with any book, apparently. I assume. I've seen a few examples. So.
Correlations are scale invariant?
Yeah.
Okay, then there's quantums.
It could be related to that. That's possible. It can explain a lot of that, yeah. A lot of that could just be due to correlations, yeah. And then there's different levels of understanding. You know, in quantum mechanics, or if you're studying quantum mechanics, you learn all the mathematics at the lower level, these symbols and equations. And if you're a student, and if you're a good graduate student, you know, you think, oh, I understand quantum mechanics because I can solve problems. But we don't really know why quantum mechanics is the way it is, or we can then quote Feynman, who said, well, just shut up and calculate, right? But then you always have the person who says, well, the higher level, you have ideas and concepts, intelligent layperson. Well, I kind of understand quantum mechanics, but I can't really do the math, right? I mean, you hear this all the time as well. In neither case does the person truly understand quantum mechanics. You really have to understand the whole thing if you understand it. You have to understand it at all scales, right? So we all need a lot of work. Science needs work. In materialism, we have a little appreciation of the fact that we don't know about everything that exists. And we don't know why the laws of nature are the way they are. And we don't even know what laws of nature are, or what it means to be a law of nature. In science, there's too much focus on laws, I think, and we often suffer from the mind projection fallacy, and we neglect descriptions and models, and we don't appreciate uncertainty in information as much as we should, I believe. And there's too much focus on isolated systems and simplicity. Systems in real life aren't isolated. They're connected, horribly connected, and horribly complicated. And that leads to, these interactions lead to emergent properties and correlations. And in physics, I think there's too much focus on mathematics and little appreciation of concepts and ideas. They're lacking a holistic view. I think that happened in the last century. I think that's why we haven't had many major discoveries in the last 100 years in physics, or 80 years. Quantum mechanics was such a big deal that it allowed us to understand so much of the universe that we couldn't even approach before. I mean, we finally were able to describe why this box is green because of quantum mechanics, right? And what physicists did is they basically took, to make discoveries, what do you have to do to make a discovery? You take the equations, and then you apply the equations to a problem, and then you can do some calculations, and you've made a discovery. That's how you make discoveries in physics, and that's kind of what we're taught. That's not how theories are made, though, except string theory. String theory is just applying mathematics to things, right? But theories come from new ideas, new concepts, new ways of looking at things, and we've neglected that in science for the last 100 years. So I guess in summary, matter matters. Materialism is helpful, but other things matter too. The humanities matter, consciousness matters, and our experiences matter. That's what we want to describe. We're interested in our experiences, so our experiences matter. And eyewitnesses matter. And not only do our experiences matter, but experiencers matter. And are all experiences physical? Maybe not. Some are. Some may just involve states of systems. That doesn't mean that's not real. And that's important to keep in mind. So Experiences are related to the physical descriptions of the world, even though the relationships between the descriptions and the correlations among them may not be understood or even commensurate. So there we go.